My name is Matt Patinio, and I'm going to talk to you a little bit more about barriers this afternoon and GPU synchronization in general. Real quick, just so you know who I am. So I've been at Ready at Dawn Studios for the last 9 years. We're an independent developer down just south of Los Angeles in California. I've been the lead engine and graphics programmer there for the past 5 years or so. In case you couldn't tell from this talk, I like talking about GPUs and APIs, and sometimes I just won't shut up about them. So I also do a lot of blogging on my blog, The Danger Zone. I'm on Twitter. Also, I got open source projects on GitHub. You might know me on the internet as MJP. It's just my initials, but I'm not very creative. So now that I got you all in this room, what is this talk going to be about? So obviously, we're going to be talking about GPU synchronization, but this is meant to be like a real introduction to them. So you might see we've had a lot of talks about barriers and synchronization across many past GDCs and SIGGRAPHs, and if you don't have like a really intimate knowledge of how GPUs work, you might not know what is actually going on when there's GPU synchronization is happening. You might know like, why do you actually need to do this to get correct results, and you might not know like what's actually happening under the hood when you do like say a transition barrier in DirectX 12. And then, a lot of the talks that talk about barriers, they really focus on the aspect of like how it affects your performance and how to like use them correctly in order to get, more optimal performance out of your games. But, you may not have a really intuitive sense of like how exactly it affects performance and in which ways. So a big part of this talk is going to be trying to help you build up like a really rough mental model of what's going on when you're doing synchronization operations, so you can know like, know generally what's going on and also how it's going to roughly affect your performance. So, any of you are familiar with DirectX 12 or Vulkan, these new explicit APIs, that barriers are a thing. And they're kind of an annoying thing, right? At least if you're coming from a world where you're just working with, like DirectX 11 and OpenGL, right? You didn't actually have to, manually issue barriers to get correct results, but now suddenly in these new APIs you do, right? And so it's actually also kind of really difficult to get right. You have to know, figure out where these kind of inflection points are for all your resources so you can issue these manual barriers. And you got to do this, otherwise you get, kind of weirdly incorrect results that vary from hardware to hardware. And as you've surely noticed, people just keep getting up at GDC and talking about them. Like, earlier today when Dominic was up here talking about how barrier performances, affects your game and how you can observe it in tools like RGP. And so, again, in this talk, what I hope you'll get out of it is you have a little bit better understanding and have a rough mental model of how, your performance is going to be affected when you do synchronization operations. So before we get into GPU stuff, we want to give you a quick overview in case you're more familiar with barriers in like a multi-core CPU programming sense. So you may be familiar with one kind of CPU barrier, which is called a thread barrier typically, which is basically a thread synchronization point. And what that means is that when you have a barrier in your code, that means that all your threads, when they hit that point in their code, they're going to sit there and wait for all other threads to get there. So usually you might spin wait in user mode or use an OS level primitive like a semaphore to get there. And basically your kind of rough visual metaphor for this is a toll plaza, but it's like a really broken toll plaza and slow where everyone's going to wait there forever instead of kind of moving through it. And then you may also have dealt with memory barriers, especially if you work on a processor that has a weak memory model like an ARM processor. These memory barriers that you use, they're all about ensuring really the correct ordering of your reads and writes, specifically with how they're observed on other threads that run on other cores. So you might want to say okay, I want to make sure all these writes have completed before the barrier point in your code, or that certain read operations happen after the barrier. And so, naturally they affect the lowest level of CPU operations that are dealing with memory, but they also will affect your compiler ordering. And basically, it will work as a signal to the compiler to say, okay, don't reorder my reads and writes, because that could potentially mess up how things are working on other threads. And so your visual metaphor in this case is like a doggy gate. It's all about segmenting where your read and write operations happen. And so you might want to be keeping your reads on one side of the barrier, for instance. So, what's the common thread here between these two kinds of barriers and also your GPU barriers? And the answer here really is it's all about dependencies, right? Where, you might have one task on one core that's kind of producing a bunch of data, and then another task on another core that's reading that data, and that naturally forms a dependency, right? You would say task B depends on task A. And so what happens when you have this dependency, it's really important. You have to ensure that you have correct visibility of your data, which basically means that when your dependent task, like task B in this case, is going to read the data, you want to make sure that it reads and gets the correct results that it expects, and that there's no race conditions or cache issues or things like that. So when you're working in the single-threaded world, you don't normally think about your data dependencies in this way, but they're totally there, right? You may compute an offset into an array and then index into an array with that offset, and then you've got two dependent operations. But you don't have to think about it because in general, the compiler and the CPU just sort of handle this naturally in a really a natural way. So the compiler can actually look at this code and see oh, I can identify that dependency, and it may do whatever it needs to make it work correctly. And also in general, you don't need any kind of if there were a need for a barrier, the compiler could possibly even put it in for you automatically. And then pretty much all CPUs will give you the expected ordering of your dependent memory operations as long as it's happening on a single core. Things just kind of work correctly in that case. Basically, this would be your easy mode, right? You don't really have to think about it. Things work correctly. This is the kind of programming you've done since you first learned how to write Hello World. And of course, you go to multi-threaded world, and suddenly everything's crazy, right? Now you've got, the thing is you've got dependencies still, right? But now they span across different threads and different cores, and it's no longer tractable to kind of automatically figure out where those dependencies are. So, because you got arbitrary numbers of threads and cores, and they can all access whatever memory they want. And so at this point, your CPU and compiler mechanisms start to break down. So the CPUs have a lot of optimizations in them at a low level to kind of optimize their memory operations. So for example, they may have per core store buffers and caches and things. And a lot of times this can cause the observed order of memory operations to come out differently on another thread. Really what I'm trying to say is everything's kind of falling apart and failing you here, and you're lost in the woods with nothing but your wooden sword, which in this case is the memory barriers in the standard atomic library. Really, you're on your own. So, a really simple case that you might have dependencies is say you've got one task, you're gonna get bread out of the cabinet, and then your next task is gonna be spreading peanut butter on that bread. So naturally there's a dependency there because you can't spread that peanut butter until you got the bread. The problem here, if we're lining this up on two cores like that, is the spreading peanut butter task is starting before the get bread task is finished, right? So you can see there's a bit of overlap there, which is actually bad in the case of dependencies. Since this overlap means that you'll have a race condition where the spread peanut butter might, try and use results that aren't actually ready yet. So what you do, the standard thing to do in this case is you would stick in a little barrier, right? And then, phew, it moves over. Now we've got no overlap. Yay, everything works correctly. You get correct results. So that kind of concept we're going to scale up to other more complicated cases. So, getting back now to the GPU, right? This is what we're actually here to talk about. The most important point, to get across here is that the GPU is not a serial machine, right? That's something you hear a lot. Of course, it's got lots of cores on it, but still we tend to, a lot of times, think of talking to the GPU in a very kind of serial way, right? Draw this thing, draw that thing, do that. And, so this is actually kind of deceiving, right? You can even, I have in here, this is a capture from RenderDoc that's showing all your draw operations happening in order. So it has this very serial look to it. And in fact, these debugging programs actually let you observe step by step what's going on as if they were serial. But in reality, that's not what's going on. So the reality is more complicated than that. There's actually a lot of hardware and driver magic going on behind the scenes to kind of extract parallelism from this serial sequence of commands. So now here, this is a timing capture from the Radeon Graphics Profiler, which if you saw Dominic's talk earlier, he was talking all about all the cool features. And this is basically showing a whole list of draw calls and it's actually showing the start and end point of when they complete, which are, there's be lots of usually vertex shader and pixel shader threads kind of all going on there. So if you look at this, you can see that especially when we've got the smaller draw calls, they're actually not completing just sequentially, they're all overlapping all over the place, right? You've got multiple draw calls that are all in flight at the same time and kind of completing all over there because, like I said, the GPU is a parallel machine. And if we look at, this is a capture from Pix for Windows, which is showing a very similar kind of thing in a slightly different way, where this was taken on an even bigger GPU. This was on my RTX 2080, and it's showing even more draw calls that are all in flight and overlapping at the same time. So you can see how, there's all kinds of overlap going on here. It's not sequential and serial. Which leads me to my next point, which is that GPUs are thread monsters, right? This is, again, it should be news, but it's important to keep in mind when you're talking about synchronization. If you look at, this is a diagram here from from NVIDIA's latest architecture, their Turing architecture, showing like a high-level diagram of like a RTX 2080. And if you look at each one of these, there's a whole bunch of little units on here called streaming multiprocessors. And if we zoom in, you can see there's also these all these little units in there for 32-bit floating point and an integer 32. So you got like 64 lanes on these SMs. And so if you multiply that by the number of SMs on a GPU, you realize there's just a ton of threads all running in parallel simultaneously on a GPU. So since these things are thread monsters, right, if you want to keep it fed, basically the best way to do that is to have lots of overlapping tasks that are going on. That way you can get better parallelism. And you can do this best when there's no dependencies, or in some cases, the hardware can actually help you out. The kind of typical case is that when you have pixel shaders writing to a render target, usually there's hardware in there that can take, even though the shaders are executing out of order and all overlap, they can actually take the outputs from those shaders, put them back in order, and then do the memory operation so that the observed results of those pixel shaders actually comes out in the API submission order, which is really cool. And of course, we do all this because, like I said, overlap improves performance, and we know that's a point that keeps getting brought up. But I'm going to go into a little bit more in depth on how exactly that can improve performance for you with some simple examples. So since we got this big parallel machine running lots of threads, that means we need some form of a thread barrier on a GPU, right? This is going to be to make sure that a bunch of threads are totally finished before another group of threads will start up again. So if you've got dependencies between two draw calls or two dispatches or something like that, then what you need to do is you need some mechanism that's going to basically wait for this whole batch of threads that would spawn from a jar dispatch and wait for them to completely run to completion. So it's kind of similar to what you might have if you use like a kind of task-based job system with a CPU task scheduler, right? Usually you have some kind of mechanism that can say, hey, I submitted a batch of jobs and I want to wait for them to all finish. So it's kind of the same thing, except in this case it's on the GPU and there's actually hardware that can do this for you. And you often see this called some kind of like a flush or a drain or wait for idle, because you're kind of waiting for all that work to make its way through the full pipeline. So in addition to thread barriers, there's also you need cache barriers, which are something that's kind of unique to GPUs, because typically or historically, GPUs have lots of little caches on them. They don't have just like a nice hierarchical cache structure like you might have on a CPU. This is changing in more recent architectures. They're actually moving more towards a unified cache structure, but historically there's all these like little caches. And the one catch about those is they're not actually always coherent with each other. This is a big change from typical CPU programming, where usually you just expect your caches to be coherent, and so that data across multiple cores will have the correct visibility. So if you look at this diagram here, this is taken from a little older AMD GCN architecture. This is prior to their Vega architecture, where at that point they have these little L1 caches here that are for the color buffers and for the depth buffers. And if you notice here, those L1s, they don't go through that big L2 there. They go right to memory, right? So this can be a problem. So if you imagine you're writing to a render target, it's going to go through that color buffer L1. But then if you wanted to read from that render target, the texture unit L1 goes through L2, and so that L2 may have to be invalidated, and the color buffer L1 may need to be flushed out to main memory in order to ensure that the render target data has the proper visibility. So this is another thing that might happen as a result of a barrier. And then of course, like Dominic said before, this is always important to batch your barriers, because if you're going to flush your cache, it's better to do it once than to do it 8 times in a row for no reason. So, and then a third kind of barrier is that you might call like a compression or a layout barrier. This was touched on earlier, but there are a lot of common GPUs now. They have built-in hardware that can do forms of lossless compression. These are mostly aimed at reducing the bandwidth needed to write to render target textures. So you can see in that diagram is NVIDIA is showing their delta color compression technology, which AMD also has their own form of delta color compression. And this is aimed at saving bandwidth in cases where you have usually the same color or value within a certain tile or region of a render target. And so when you have a texture that's in this compressed format, or a depth buffer even, you may have to decompress this, possibly, depending on the hardware, in order to read it as a texture. So if you have a barrier that's changing from like a write state to read state, you may need that kind of decompression operation happening. It's also possible there may need to be some kind of decompression or compression disabled entirely if you're going to write to that texture through unordered access view, because may not be going through the same hardware that the render target writes are going through. So if we bring this back to D through D12, if you have any experience with it, you'll know that they don't actually work on this kind of low level, right? You don't issue cache barriers or thread barriers. Instead, they work at a kind of higher level in abstraction, which makes sense because it's an API meant to talk to lots of different hardware, so it wouldn't make sense to leak through all this like hardware-specific details into the API. So instead, it works with this kind of resource state abstraction, right? It's mostly about saying like whether it's a resource can be readable by a particular kind of pipeline stage or writable by another pipeline stage, and really what you're describing is the resource visibility. And from that visibility data, the driver can kind of infer the implicit dependencies from your different transitions, and can also infer the layout and compression operations that might be needed to kind of make things work for the barriers you've specified. And then Vulkan it's Vulkan similar, or it's just a little bit more explicit and verbose than what you have in D through D12, but you're still kind of having a higher level abstraction. You just have to supply a little bit of extra info, you have to be more specific about the producing and consuming GPU stage and whether it's in a read-write state, and also there's some options for manually specifying texture layout. But again, both of these are really about abstracting away the GPU specifics, right? But despite that, you're still kind of, since you're manually issuing the barriers, you're still in the driver's seat a lot of times in terms of what these kind of different operations are happening. You're just going through a little bit of an abstraction. And so as a result of that, since you're manually issuing the barriers, you're going to be able to oversync or flush or decompress. So you have to be real careful about how you use your barriers. And the good news about this is that AMD's Radeon Graphics Profiler will actually show you what's going on whenever you issue a barrier. In terms of it'll show you like what thread synchronization is happening for what shader stages. It'll show you which caches it's flushing and invalidating, and it'll also show you the source of the barrier, because in some cases, most of the time you're actually explicitly issuing a barrier, but there's certain cases where a barrier may be applied by other API calls. And then Pix for Windows has a really awesome feature too, that when you take a capture, it can show you these warnings that show you when you're not batching your barriers. It'll show you that, oh, hey, you've got consecutive calls to resource barrier, which is saying, hey, you should be putting these into one call to resource barrier to batch them up. So what about D through D11, right? Like we said earlier, you really didn't have to worry about any of this stuff with barriers and synchronization. And the reason why is because actually, the barriers were actually there, they were just hidden from you, right? They were all being handled by the driver. And the driver was mostly doing this by tracking dependencies for you automatically behind the scenes. It's sort of like this big runtime compiler that was analyzing all your D3D commands that you submit for a frame and then saying, oh, here's this dependencies, I need to do this transition on the depth buffer, and doing it automatically. So again, this is like easy mode. It was saving you the work of having to think about this. The big catch here is that this is a ton of CPU work for the driver to be doing, right? It's got to analyze all the stuff, figure out the barriers, and it's usually they do this by having these kind of like driver threads running on your other cores, so that's a ton of overhead there. And then another big kind of downside of that is that doing this kind of automatic dependency analysis is just intrinsically really hard to do with multi-threaded command submission. This is because dependencies, you may split up your frame into 5 parts and do those across multiple threads, but your dependencies might span those different parts of your frame, and so this kind of suggests that a driver will have to serialize and put together your different parallel submissions into one big kind of frame submission list in order to figure out dependencies and insert the barriers for you. And then finally, since it's got the driver has to know your dependencies and track them, this also implies that there's some sort of, CPU visible, API-driven resource binding, like, it's some kind of explicit, like, hey, bind this texture to the slot for the shader stage. So this basically precludes the newer, fancier, more awesome, bindless models that we can do in DirectX 12 and Vulkan. So yeah, all three of these things are basically fundamentally incompatible with the ethos of, DirectX 12 and Vulkan, which are all about, enabling the lowest possible CPU overhead and allowing you to do multi-threaded command buffer submission, and also enabling these new fancy bindless resource binding models. So now to dig in a little further and talk specifically about the thread synchronization part, I want to kind of, I thought it'd be helpful for this to, instead of looking at a real GPU, which is very complicated, to actually kind of look at a more simplified GPU that has a lot of the basic traits of how GPUs do thread synchronization, but is got kind of stripped down a bit so that you can follow it more easily in a presentation like this. So I introduced to you the MJP 3000. It was designed by yours truly. This baby's got 16 shader cores that you can see labeled on there. That's a whole lot of compute power. It's got some memory. Over on the left side, you'll see there's a command processor, which basically will process one command at a time. And then it'll use, basically those commands it'll use to deposit a bunch of running threads into a thread queue. So together that command processor and thread queue would form what we'd normally call like a front end, because those will feed into the shader cores, which do the heavy lifting. And then in the top left, there's the current cycle count, which will basically let you follow along like how much time has elapsed as I go through some examples here. And then broadly speaking, the command processor over on the left is what I'd kind of would call the brains of the operation. This guy is going to be able to process different commands and is mostly going to be responsible for the scheduling and figuring out which work should actually run. And then meanwhile, the shader cores is what I would call the muscle, because these guys are doing all the heavy lifting. They're not smart. They just do what they're told and they just run things, but they are actually doing all the work. And some limitations that this has compared to like a real world GPU is that we're only going to do compute shader dispatches. So despite me calling it GPU, we're not actually going to really do any graphics. But that drastically simplifies things so we don't have to include like a rasterizer and all the different rendering stages. And like I said, there's only 16 shader cores, which is quite a bit fewer than you would see on a typical desktop GPU or a console. And there's no SIMD on here, so most GPUs will leverage SIMD in order to drastically increase their throughput, but there's no SIMD on this guy. The 16 shader cores can be just considered completely independent, which means they can each run their own different shader program if necessary. There's also no thread cycling, which is something you normally see on GPUs, where each kind of shader core can run for a bit, then switch to another thread, which it'll normally do to try and hide the latency of long memory accesses. And finally, there's no caches on here, because that's also going to simplify things. We're not going to talk about cache barriers for this next part. We're just going to look at thread synchronization in depth. So let's run through a simple example on the MJP 3000. So let's say we're going to dispatch just 32 threads, and each one of those threads is going to write one element to memory. And each one of those threads we'll say takes about 100 cycles to complete. So if we run through this, we start out, we've got the dispatch A. It's got 32 threads. Once that gets processed by the command processor, we'll get 32 threads deposited into the thread queue, which now is sitting there. And then when there's threads in the thread queue, the shader cores will pull out some threads to actually execute. So now we've got 16 threads that are all executing on the shader cores, and then 16 threads remaining in the thread queue. So these, like I said, this particular shader program is going to take about 100 cycles to complete. So if we jump forward 100 cycles, all those threads have finished, and they've written the results in memory over on the right. And now the remaining 16 threads in the thread queue can hop on the shader cores and have their turn. And so they're going to take another 100 cycles, and then they're going to write the results to memory over on the right. So the whole thing took 200 cycles. All right, so let's try an actual example with some synchronization, because that's what we're here to talk about. So let's say we got two dispatches now. We're going to have dispatch A, which is again going to be colored in red, and then we're going to have dispatch B colored in green. And we'll say that dispatch B is dependent on dispatch A. Basically, dispatch B is going to read the results of dispatch A. Because of this, we can't have any overlap, right? Because we want to avoid race conditions. So we'll introduce a new command, which we'll call flush. And this flush command will basically cause the command processor to just spin and wait for the thread queue and the shader cores to become completely empty. It won't process any further commands until basically all the current threads in flight run to completion. So let's try that out. So we'll start out with dispatch A. We got 24 threads of dispatch A that we're going to get in the thread queue, and then have 16 of those threads will end up on the shader cores, and we have 8 threads left in the thread queue. So we jump to 100 cycles later, that batch is finished. There's now 8 threads left of dispatch A that are running on the shader cores. And if we look at the command processor, you'll see that it's on the flush. So it's basically going to wait for these remaining 8 threads to make their way, to actually completely finish before it moves on to dispatch B. Because of that, there's no overlap going on. There's no threads from dispatch B happening simultaneously. But this also means that half of our cores are sitting there idle. So we've got essentially 50% utilization for this portion. So if we jump another 100 cycles later, that batch of 8 threads is finished and get written to memory, and now the command processor can move on from its flush and start working on dispatch B, which has another 24 threads that will make their way into the thread queue. And then finally onto the shader cores, 16 threads will get processed at a time. That'll take 100 cycles. And then at cycle 300, we got the remaining 8 threads from dispatch B that are now on the shader cores. And again, we got 50% utilization for this portion. And finally, the whole thing's done at cycle 400. So let's see how we did on this. So the flush worked, right? It gave us correct results by preventing overlap of dispatch A and dispatch B, which is cool. That's what we wanted. But on the downside, the cores were basically 50% idle for 200 cycles out of the full 400 cycle kind of, we'll call it a frame here. So that means we got 75% overall utilization. So it took 400 cycles for this whole thing, where if you think about it and we didn't have the barrier in there and we just had full 100% utilization for the whole time, that would have taken 300 cycles. So it cost us quite a bit to have that barrier in there. So that leads us to think, all right, so how do we kind of have a mental model for how much a barrier costs? Well, one thing to keep in mind when you're doing that is that the barrier cost is basically relative to the drop in utilization that you get from inserting the barrier, right? So the amount of idle cores it causes is basically going to be your cost of a barrier, at least in terms of thread execution, not counting for caches and things like that. And then if you flip that around, we can also kind of surmise that the gain from removing a barrier is roughly relative to the percentage of idle shader cores that you had from having the barrier in the first place. So the more idle cores you have, the more potential to speed things up by removing a barrier or optimizing it in some way that's not necessary. And then this also leads us to the conclusion that having larger dispatches is generally better for having a higher utilization, because you're going to have more threads to kind of just keep the shader core saturated. Whereas if you have smaller dispatches with longer running threads, these can give you a very high flush cost, right? Because if you have a very long running thread, that makes it more likely you're just going to have the command processor sitting there waiting on that flush with less than 100% utilization. And so it's also important to keep in mind so that when you are doing a transition or pipeline barriers in D3012 or Vulkan, they're generally on most common hardware going to lead to this kind of like global flush operation. You can generally expect some kind of at least a per stage thread flush for whenever you issue a transition or a pipeline barrier between a pair of draws or a pair of dispatches. So generally you're going to have this kind of thing where the command processor sits and waits for a whole group of threads to completely finish, and you're going to have a period of idle time there because of that. And then it's also the same for if you do the UAV barriers that are available in D3012, which has similar implications, because that's implying that you want the data written to you into a UAV from a dispatch or draw to be visible for any subsequent dispatches or draws. And so you should really try and always group your non-dependent draws and dispatches. So if you have things that don't have dependencies, it's great if you can group them in with other things that it's not dependent on between your barriers. That gives you kind of more threads to kind of keep things occupied and possibly increase your utilization. And of course, you should keep in mind too, what I'm talking about here is more about kind of current existing GPUs you'll see and like that users have in the market or that are available right now. In the future, things could be totally different. There may be finer grained synchronization operations available in hardware. I'm kind of more just talking about what's currently available right now, so keep that in mind. All right, so let's try another example where this time we're going to try and do what I said. We're going to try and overlap some non-dependent work with our previous example to try and reclaim some utilization. So we'll start with our previous example where we have dispatch A is dependent on, dispatch B is dependent on dispatch A. And then we'll throw in another dispatch in a mix that we'll call dispatch C, colored in blue. So this guy's not going to be dependent on either of them. So we're going to try and throw them in to reclaim some of those idle cores we had. So yeah, like I said, we're going to try and recover some performance and hopefully, increase our utilization percentage. So we'll start out. So we got dispatch A. We got again 24 threads here that are the command processor will process that first. It'll get those the first batch of 16 threads from program A. We'll make it on the shader cores. And we got another 8 threads from program A in the thread queue. And then the command processor has already processed dispatch C. So we got 8 threads from dispatch C in the thread queue also waiting to go. And if we jump to 100 cycles later, the first batch of dispatch A's threads is completed. And at this point, we've got the remaining 8 threads from program A, but the threads from dispatch C were able to kind of sneak in there and take those remaining cores and keep them busy instead of leaving them idle like we had last time. And now the flush is also going to wait for all this work to complete, which will take another 100 cycles, and then dispatch B can start working on and get its threads into the cores. So that'll take 100 cycles for that batch of 16, and then another 100 cycles for those last 8 threads to finally finish and write the results to memory. And so the whole thing took about 400 cycles, and everything's complete. All right, so how did we do this time? you may notice that we basically had the same latency for dispatch A plus dispatch B, right? From the start of dispatch A to when dispatch B was completely finished, it took the same amount of time, which is 400 cycles. However, the nice thing is we basically got dispatch C for free, right? We kind of just snuck it in there. It took up those idle cores, and it completed, and we didn't actually increase the total running time. So our overall throughput increased because we got more done in the same amount of time. And if you were to think about it, if we were to do this sequentially, where if we did A plus B plus C with barriers in between, that would have taken 500 cycles. So we basically saved 100 cycles by doing it this way. And our total utilization went from 75% to 87.5%. So that's cool. We got more out of our hardware, basically. So what insights can we kind of draw from this example and the previous ones, right? So what if we were to kind of like, you take off your glasses, squint a little bit, and you kind of think like, okay, the GPU, it's not that different from a CPU. What if I think of it as this whole thing as a CPU, right? You can kind of think of each command that's submitted to the GPU as a single instruction that a CPU would execute. In that case, then, overlapping is kind of similar to instruction-level parallelism, which is something you get on a lot of modern processors, where you get multiple different instructions that are actually getting processed in parallel, even though they were kind of issued sequentially. The one catch here is that this is kind of mostly explicit, right? We had to explicitly schedule things and schedule our flushes in such a way so that we got the overlapping. So in some ways, it's kind of similar to some of the crazier, very long instruction word architectures out there, where also in that case, the compiler was mostly responsible for identifying dependencies and figuring out where non-dependent operations could be snuck in usually on like kind of SIMD-like hardware. So in that last example I showed you, so that worked out great. We had this dispatch C that slotted in perfectly, but you could probably easily imagine a case where that's not actually going to work out so well, right? What if dispatch C took longer? In this case, we're going to say, all right, what if dispatch C takes 400 cycles this time? That's going to really kind of mess things up quite a bit. So let's see how that actually shakes out. So we'll start again with dispatch A. We'll get the first batch of dispatch A and the shader cores. And if we jump to 200 cycles later, go fast forward a little bit, we see, oh no, what's going on here? The command processor is waiting on a flush, so it's waiting for everything to make its way through the shader cores. But since dispatch C is really slow this time and takes 400 cycles, it's still kind of sitting on there parked on the cores. And so, when we've got to kind of now wait for dispatch C to finally finish before we can move on to dispatch B, and for that whole time, we're going to have only 50% utilization with half our cores remaining idle. So we can't finally move on to dispatch B until cycle 500, and then now we can kind of proceed as normal, get the first 16 threads up on the shader cores. 100 cycles later, we do the remaining 8, and then the whole thing finishes at cycle 700, and everything's in memory. So yeah, what happened there? That did not go so well. So we had 400 cycles where we only had 50% utilization, and half our cores were sitting idle. So that drops our total utilization for the whole sequence down to 71.4%, which is pretty bad. So we tried to, kind of sneak things in and overlap them, but instead we just made it worse. And really the problem here, if we identify it, is we only got one front end, which means we only got one command processor, we got one command queue, and so this kind of turns all of our flushes into a global flush or sync. This is a pretty blunt instrument to work with for synchronizing things. Every time we're going to do a flush, the command processor is just going to sit around and wait and not be able to move on to anything else. And so in this case, we really just wanted B to synchronize on dispatch A, but it ended up also synchronizing on dispatch C because of the way that works, so that was bad. And then, rearranging or, possibly splitting things up could help a bit, but it's, it's not going to totally fix the issue depending on all possible configurations, right? Because you don't necessarily always know how long any dispatch threads are going to take or, how things are going to scale across different hardware or different resolutions and things like that. So if one front end, one command processor is our issue, then you might think, okay, why not two? Let's just throw another one on there. Then we can do two things at once. And it's not as crazy an idea as it sounds. So the engineers at MJP Industries, they received your feedback. They took the idea in, and they said, all right, we are just going to shove a second front end on here. It's got its own command processor and its own thread queue. And once they did that, they realized they messed up, and they ran out of their transistor budget, and they couldn't actually stick any more shader cores on there. So they said, oh, no, we're stuck with what we have. We're still at 16, but hey, at least we got these two front ends. So maybe that'll help. So, looking at this, this new beast of a machine. So as we saw, there's 2 front ends on there. So now we can do 2 sync operations and 2 commands processed at once, and also 2 thread queues to feed into our shader cores. And what the key here is that now basically this enables us to have 2 independent command streams, right? So if we have 2 command streams that aren't going to sync with each other, they just may have synchronization within a command stream. This is what we can run on this guy now. And again, independent really is the key word here to focus on. And like I said, we still only have 16 shader cores, so our max throughput hasn't actually increased versus MJP 3000s. So if we're going to be, if we hit 100% utilization, we can't really beat that. We'll still be bottlenecked by the shader cores. And then we're just going to use a very simple, like first come, first serve system for resolving conflicts between the 2 thread queues. So basically, whatever thread queue gets threads first will get on the shader cores. And if they both get there at the same time, the shader cores will just split evenly between the 2 thread queues. So let's try a simple example. All right, so let's say now we got dispatch A. It's got 68 threads, and each one of those takes 100 cycles to complete. And then we got dispatch B, which is kind of a non-ideal case. This is only 8 threads, and it takes 400 cycles. So on its own, it could not saturate the 16 shader cores. And we got B is going to depend on A, so there's going to be a flush in between them. And now let's say we also got dispatch C, which has 80 threads, and each one of those takes 100 cycles to complete. And then dispatch D, which is kind of the same, 80 threads, 100 cycles to complete, where D is going to depend on C. So this gives us essentially 2 independent command streams, which is cool. This is what we want to kind of feed our dual command processors on the GPU. So we're going to try that. We're going to submit these as 2 different command streams and see how it goes. So we'll start out at cycle 0. We're going to submit the first command stream with dispatch A to the top command processor. And then, if we jump to 50 cycles later, we can see the shader cores are already working on the threads from dispatch A. And at this point, we're going to submit our second command stream to the second command processor. So since the shader cores are already tied up with dispatch A, there's just going to be 80 threads from dispatch C that'll get deposited on the thread queue, and they'll wait there until something opens up. So we jump to cycle 100 now. The first batch of dispatch A's threads have completed and written the results to memory. And now the shader cores are all free, so they're just going to, since there's threads in both thread queues, they're just going to pull from them evenly. So we've got half the shader cores are being used for dispatch A's threads, and half the cores are being used for dispatch C. They're sharing so nicely. And then if we jump way later to cycle 600, we can see now dispatch A is basically winding down. So it's only got 4 threads left at this point. So normally, if we were syncing on dispatch A and we didn't have the other command processor, we would have only 25% utilization here. But since we have the other thread queue that had a whole bunch of threads waiting, we can now dispatch C can kind of grow and take up 3/4 of the shader cores, and we can stay at 100% utilization, which is cool. We're going to keep getting things done. And then we jumped another 100 cycles. We got, dispatch C is using all the shader cores now. They're kind of churning away on that. And dispatch B has made its way into the thread queue because the top command processor finished its flush. And then if we jump another 100 cycles later, now we've got dispatch B is now its threads have made it on the shader cores. And again, like I said before, it only had 8. So on its own, it wouldn't be able to saturate all our 16 shader cores, but since dispatch C is still going, it can use those remaining 8 cores, and we can keep high utilization. And at cycle 900, dispatch C is winding down. It's only have 4 threads left, so we get 75% utilization here, which is not great, but still pretty good. And once that finishes at cycle 1000, now dispatch D finally has its turn. The flush finished on the second command processor. So now the threads from dispatch B can make their way into the thread queue and out to the shader cores. And they're going to just basically share it with dispatch B for a while until that finishes. And then around cycle 1200, finally, dispatch B has totally finished. So now dispatch D has free reign of all the shader cores, and it'll just keep using them all the way until cycle 1600 when it's all done, everything's in memory, and we're finished. Whew, that was a lot. So did 2 front ends help? I would say, yeah, it totally did. We got that worked out great. We got 98% utilization out of that, which is way higher than we had in some of our previous examples. And we didn't even increase our cores, right? And we're getting better throughput here, which is really cool. And then, so basically what we got here is the lower total, the total execution time of, completing A plus B plus C plus D was lower than what we would have if we were to kind of submit those all sequentially on one command processor, which is cool. So that second command processor helped us get that higher throughput and basically give us a lower total time of execution. But the one drawback is that we did have higher latency if you were to look at just A plus B or C plus D individually, right? Since those guys were kind of sharing the shader cores in there, they took longer than they would have if you only had one submission to one command processor. But if you care about optimizing everything holistically, this is a good thing, right? We've kind of got it's kind of like thinking about it. You want to have a lower total overall frame time, even if it takes longer to do one operation like SSAO or something like that. And then on real GPUs, potentially it can be even better. It's more complicated, obviously, because like I said, there's a lot more going on with caches and memory, and you saw some of this in earlier talks. But you can have threads stalled on memory access on real GPUs, and then so what'll happen is, like I said, they'll do thread cycling. So if you have extra work coming in from other command processors, that can potentially give more threads for these shader cores to switch to, which is cool, and then they can hide latency better. You also got, you'll have idle time on real GPUs that are caused by flushing those caches. That takes time where the command processor will just sit and wait before launching off new threads. So if one command processor is sitting and waiting on a cache flush, then that's a good opportunity for another command processor to throw in some work and use the shader cores. And then also you have, kind of naturally, you have tasks that generally don't use the shader cores a whole lot, right? You got one case is depth-only rasterization, which you do for, like a Z prepass or shadow map rendering. These guys mostly only exercise the fixed function units for rasterization and for writing the depth buffers. So if they're not using the shader cores, that's a great opportunity to throw in some other work, compute work that can actually use the shader cores while they're idle. And then you've got some other situations like certain forms of doing, like trying to keep tessellation or geometry shaders on chip instead of spilling them to memory can lead to these kind of natural serialization point where the work can't spread out to lots of different shader cores. And so that's another case where it could be good to have some extra compute work from another command processor to throw in there. And then finally, there's also usually fixed function DMA units on GPUs, and those guys don't use shader cores at all. So if a command processor is waiting for one of those to finish, that's also a good period where there might be idle shader cores. And if we were to once again think about this in CPU terms to kind of relate it back to there, having this kind of concept of multiple front ends is kind of roughly similar to what you get with simultaneous multi-threading, which is a common feature on CPUs these days. You might see it called hyper-threading on Intel processors. And what this what this setup does is it basically tries to interleave two different instruction streams, usually two different threads that will they'll share the actual execution resources that actually execute the instructions, that do the memory operations or doing like the arithmetic. And what the goal here is basically to try and the CPU will try and reduce the idle time from stalls, from like cache misses and things like that by having another thread to switch to. So really it's kind of similar to our goal with having two command processors on a GPU. Basically you're trying hide or make use of idle time by getting some other work done from a non-dependent command stream. So if we're to kind of look at it like an actual real-world example now, right, that you might see in an actual typical game engine, this diagram's kind of showing like a typical post-processing stack, right, where you might have you might do a main pass that's like forward rendered to an HDR render target, and that'll feed into two different post-processing operations. And even though these are two different operations, they actually consist of many sub-steps. So Bloom is pretty common, something you'll usually do by like downscaling a couple times and doing a couple separable Gaussian blurs. And then depth of field is another thing that usually is broken up into a bunch of steps where usually you do some kind of like, computing the circle of confusion for depth values, and then maybe doing a downscale for performance, and then doing like a fancy bouquet-shaped gather pattern. And so, these are two different post-processing operations that they have dependencies within each other, but they're actually independent in terms of each other's like total operation, right? The Bloom is basically independent of the depth of field here. So this looks like a good opportunity for moving these to two different command processors. So if we kind of do that and rearrange it like this, right? So this is how we might like execute it on the two command processors of the MJP 4000, where you might have like all these, you have these different operations that they do require a command processor local flush, or we might also call it like a queue local barrier, right? So these guys here, these are basically resolving dependencies within a single command stream. And then when we would also really need to do this right is we need some kind of like cross queue barrier, right? Because we got to make sure that we don't start the depth of field process on the second command processor until the main pass is finished. So we also need that kind of synchronization. And this actually, maps pretty well to like what you have in like DX12 and Vulkan. So, in DirectX 12, your application will record and submit command lists, and then you'll use these kind of fence objects to synchronize them when they're submitted. And what happens is, whenever you submit a command list to a command queue object in DX12 under the hood, the OS has basically a GPU scheduler. And this GPU scheduler will receive your submissions and it'll be like, hey, I'm going to now schedule it to run on an available command processor or hardware queue on the GPU itself. And these show up in the terminology the Windows driver stack uses is they'll call each one of these GPU hardware queues an engine, where an engine is either like takes a form of like a direct, which can do all the graphics operations and compute operations, or like a compute engine, which can only do compute dispatches, or a copy engine that can only do copies, usually through DMA. And there's also a fourth type, which is a video engine, which you generally don't interact with through DX12, but that does like video encoding and decoding operations. So basically, you have these engines that are exposed to the scheduler, you submit your command list, and then the scheduler will run them on an engine, which generally represents a kind of a hardware queue for your command buffers. And so, and then usually on the other end of that hardware queue, you have some kind of command processor that will actually, execute your commands and do your work. So if we were to take our earlier example of the bloom and depth of field, now we map this into kind of DX12 language, we get something like this, right? So we've got a direct command queue and a compute command queue. And so we're going to have on our direct queue, we'll do our main pass, because that's all graphics stuff, and that's going to be one graphics command list, and we'll have another command list to run on the direct queue that does our bloom, and then finally the tone mapping is its own separate command list. And meanwhile, we're going to map our depth of field to a compute command list, so these will be all dispatches, right, since the compute queue can only do compute operations. And you can see on there's these in those purple boxes, there's a B, which is indicating that these are where our barriers are. That's where we'd put them, because generally we'd have dependencies between like the downscale operations. And then we've got fences there to do our our cross queue synchronization that'll help make sure that our individual submissions actually execute when they need to. So if you do this, this is a good fit for a lot of hardware, right? Because, your common AMD and NVIDIA hardware will have usually, at least one kind of graphics front end and usually multiple compute front end. So doing this kind of setup where you submit to a compute queue is a good way to make use of that hardware. It's just one thing you got to keep in mind if you're going to do this, and your goal is to try and increase utilization, by having an extra compute submission to use up your shader cores. It's totally possible that your different submissions will end up running concurrently, but it's not at all guaranteed because there's all the complexities. I mentioned there's a whole OS scheduler in between you and your submissions and the actual hardware. So it really depends on how that all works out. The scheduler's got to decide to run your commands simultaneously, and the GPU and the driver have to actually expose, engines for the scheduler to run your commands on. And so it's kind of similar to threads on a CPU, right? You can make as many threads as you want, but there's not actually a guarantee they're going to all run concurrently on separate cores. It's totally possible there's only one core and your thread's just kind of serialized, and you can have the same thing on GPUs, so you have to check on that usually with special tools. To kind of enable all this with the scheduler and the engines and everything, DirectX 12 really is like virtualizing your queues under the hood. So it's important to keep in mind that a command queue object is not a direct mapping to a hardware queue. It's more just a plug into the OS scheduler. So since a hardware out there, it might only have it could have lots of compute queues, or it could have no compute queues and only have one queue that does everything, right? And so the OS and scheduler, its job, it will kind of figure this out for you in DirectX 12, which is kind of cool. So if you submit lots of command lists of different queues, the OS will figure out a way to make it work, which it may do by actually flattening your submissions to different queues and actually submitting them all to one hardware queue. And it can do this because your fences are only in between command buffer submissions and not inside of them. And also, since your fences kind of give global visibility of your dependencies to the scheduler, so the scheduler can figure everything out, can even do things like detect deadlocks for you. But that also makes fences kind of a heavyweight operation from a CPU point of view because they're actually feeding into the OS. So you got to be careful about using too many of them. And then if you want to know what's really going on, you should always check GPU View is a good tool that can show you how your actual CPU and GPU work is getting executed. Pix for Windows is a timing capture that can show you how actually things are correlating on the GPU to where your submission points are in the CPU. Radeon Graphics Profiler has another good view that's similar to that. And Insight also has like the thread trace and such that can show you all kinds of detailed info about how and when your work is actually executing on the GPU. So you should always check that to see how things are going and how they're stacking up. And then also keep in mind that Vulkan queues are actually a little different than this. I was talking about DX12 for a while, but the Vulkan queues are not exactly virtualized in the same way. They have a little bit of a different interface. So what you have to do in Vulkan is you actually have to query at runtime for what queues are available on the device, and it'll say like, hey, this device has 1 graphics queue and 8 compute queues. And then you have to basically, when you create your command queues to submit to, you have to bind to those slots that are available and exposed on the device. So because of that explicit bind, you have to really change how you break up and submit things. So if you're planning on doing like, oh, I want to do 4 compute queue submissions, and then it turns out the hardware doesn't, or the device doesn't expose any compute queues to you, you have to figure out how to flatten it yourself. Whereas DirectX 12, it will do it for you. It'll find a way to do it. But either way, still, like what's exposed and the Vulkan device is still not, it's not guaranteed to be exactly, one-to-one with a hardware queue. So you shouldn't assume that to be the case. So yeah, so generally, like I'm saying, this technique, and everyone we call it async compute, right? Which is basically you're going to try and leverage the extra compute front ends on GPUs to schedule some compute work that can hopefully parallelize and fill in the idle cores that are left on your main graphic submissions or other compute submissions. So if you're going to try and do this to improve your frame times, you're basically you're going to try and fill in the idle shader cores. So really, it's going to work best if you can find out where your cores are idle and fill them in, just like we did in that example we had earlier in the MJP 4000. It's that same concept. It's just more complicated. There's a lot more details, but that's kind of the rough basis of it. So, and to do that, you really want to also identify your independent command streams, because that's going to be your opportunities to submit them as on separate queues. So if you basically what we're going to want to look for is like kind of longer streams of commands that to each other don't have dependencies, but they may have dependencies within your single command stream. So like like I showed before, your bloom and depth of field were kind of like perfect examples of that. And of course, it's going to work best when you have lots of idle shader cores, so you should look for those kinds of opportunities. Like I mentioned already, depth-only renderings, the classic case of idle shader cores, or if you got lots of barriers on one of your queues, that's going to be places where you can hopefully like sneak in some async compute that will utilize idle shader cores. All right, so just a quick recap to make sure I drive the important points home. Number one, so your GPU barriers that you issue, they're basically going to ensure your data visibility. That's what they're all about. That's why that's why you have to do them. So, they're probably going to involve some kind of, GPU thread sync, especially if you got a barrier in between like 2 dispatches or 2 draw calls. Possibly, depending on the hardware, they may involve a cache flush or an invalidation too. So you should watch out for that. And then they're also, depending on other hardware-specific things, they may involve some kind of data transformation or layout change, which is typically some form of a decompression operation. So that can also make things more expensive than usual. And really, when you're submitting your barriers in D3D12 and Vulkan, you're really describing your resource visibility and your dependencies. So really, if you want to do, kind of try and optimize your barriers and reduce them as much as possible, then you should be thinking carefully about what your dependencies are throughout your frame. It can help to visualize this by like kind of graphing them out. Then you can naturally see where your big sync points are going to be. And it's also possible to do things where you kind of like use like a frame graph structure that'll automatically determine your dependencies for you, which is similar to like what D3D11 was doing. But hopefully, if you're doing that in your own code, you can do it faster, and then you can issue the correct and most optimal barriers. The other big point I would want to drive home is that GPUs aren't really that different, at least compared to like your typical multi-core CPU programming. You can think of your command processor as basically like kind of a hardware task scheduler, right? It's just kind of orchestrating work that's going to get scheduled to run on the shader cores, which, instead of your shader cores are basically to take the place of your worker threads or cores, what you would have on a CPU task scheduler. And then, you really have some of the same problems when you're doing multi-core CPU programming. You still have like parallel operations in flight. You got to make sure you avoid race conditions by putting in the right barriers. And you can still have some like coherency and memory ordering issues that you have to deal with, and those require also putting in manual barriers in your code. And the third point is that, in general, having barriers is going to lead to, idle cores on your GPU, which is, makes your GPU sad. So, you want to really keep the thread monster fed. It's very hungry. It's got a lot of cores, so you want to, minimize your barriers. So, because every barrier is going to lead to like a wait or a stall, which is going to decrease your utilization. And so, naturally, having careful barrier usage is going to lead to much higher utilization and hopefully higher throughput and lower frame times. And then always watch out for like really long running threads, especially if there's not many of them. These guys can lead to, natural points during your frame where you're syncing on this like long thread, and there's not really much else going on in the GPU. That's not making optimal use of a big parallel machine. And then of course, like everyone said 100 times, always batch your barriers, because flushing your cache once is always going to be much, 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 much better than flushing it multiple times in a row. And if you are going to be adventurous and try and use multiple queues, remember that, doing multiple queue submission, you may get, they may execute in parallel, and it may improve your utilization, but it depends on a lot of factors. So you should always check your tools to see what's going on and make sure you're actually getting a benefit from it. And then of course, it's not going to magically increase your core count. So if you have places where you're already bottlenecked by the GPU's natural resources of its shader cores or its memory bandwidth, that's not going to increase by submitting to multiple queues. That may even make things worse depending on what kind of work is happening on your different queues. And then you should always, be looking for your kind of independent command streams, right? Your groups of commands that don't have dependencies on another group of commands. That's going to be your best cases for submitting them on separate queues. And then also you want to be careful, you don't want to go crazy on D3D12 with fences. Each one of those fences is very heavyweight from both a CPU and GPU point of view. So you want to, be careful to balance that. So that's it for my talk. Just, wanted to give a quick shout out to the advisors on this talk, as Steve Tovey, Reese Sommerfeld, who helped me get in the talk, Nick Thibieros, and Andrea Tatarino from NVIDIA, and then everyone at Ready at Dawn that watched my run through and gave me a lot of valuable feedback. If you want to reach out, my work and personal email are up on there, as well as my Twitter. It's also a link to my blog. If you hadn't read it already, there's a big series of blog posts on here that's on this like kind of same subject that just goes into much more detail, so feel free to read that. And also it's a link to my GitHub where I got all kinds of open source projects you can check out. So at this point, if anyone has any questions, feel free to come up to the microphone.
Hello.
Oh, hi.
Do we have a chance to manipulate the priority of the queues?
I'm sorry, could you repeat that?
Can we manipulate the priority of the queues?
The already?
Priority.
Oh, priority queue. Oh, I don't think so. None of the APIs actually expose the ability to set a priority for queue. Well, there is one in D3D12. To my knowledge right now, there's just normal and high priority on D3D12, and I believe it only affects the actual scheduler within the operating system. So it doesn't actually, I don't believe the current GPUs and drivers actually do anything with that information, but so it actually only comes into effect when, at least in my experience, when you have hardware that doesn't have multiple queues and the OS is flattening them, right? So say if you had a graphics submission and an async compute submission, and so the OS will basically do one and the other, and then if you flag the priority, the OS will just kind of flip it around and we'll submit one before the other. And when it does that, I haven't actually seen it have any effect on like AMD or NVIDIA hardware that support async compute or anything like that. But I'm not 100% sure if it's true or not, so I don't want to totally take my word for it. All good. All right, then. Thank you very much. Thank you for coming.